Welcome to Fluid Mechanics N6. Today's video is a video on flow in pipes, and this will usually constitute the first question in your exam. And so please pay attention because the stuff from question 1 in your exam paper is actually derived from this module. Let's begin. First, we will talk of the two types of flows that you have in fluid mechanics. The first one is turbulent flow. So we say that a flow is turbulent when particles that are flowing do not maintain their position relative to each other. So it is a flow that is disorderly. So what I mean by that, if you look at the picture that I have here, the lines that you see inside of the flow, these are the lines that particles are following, okay, as they are flowing. These are the lines that they follow as they flow. So now, if we look at the two particles on top here, okay, the one following that line and the one following the line here, okay? So if you look at those two particles and you try to measure their position or the distance between them at specific locations, you will see that it is not remaining constant. What I mean by that is that if you measure at this cross section the distance between these two particles, you will have that distance there. But then if you come at this cross section and you try to measure the distance between the two particles, you will have that distance there. So they are closer here than they are here. Okay, and so for that reason, you can see as the fluid is flowing through the pipe, these particles are not maintaining the same position relative to each other, okay? And so it is a flow that is disorderly, and for that reason we will refer to that kind of a flow as a turbulent flow. The second type of flow that you will have in fluid mechanics is what we refer to as a laminar flow. Now, what really makes this very important is that this is the flow that you will deal with for the most part in your fluid mechanics N6. Okay, most of the flows we're talking about are just laminar flows. And in a laminar flow, particles are flowing in streamlines, and the flow is orderly, and the particles are maintaining the same position relative to each other. And again, if you look at the picture here, you will see this is a picture of a laminar flow, okay, a good representation of it. And you can see the lines of direction of each particle that you have in the flow. And if we were to measure the distance between two particles, maybe at this cross section, you will have that distance. If you come somewhere down in the direction of the flow and you measure again, you will see that the distance between the two particles is the same. So particles are maintaining their positions relative to each other, okay? And if that is the case, then the flow is orderly, and that is what we will refer to as a laminar flow, okay? So before we move on, there are a few terms that we need to become familiar with as far as fluid mechanics N6 is concerned. The first term is uniform flow, okay? So when we say that a flow is uniform, what we mean by that is that the velocity and the cross section of the fluid that is flowing remain constant, okay? So you could go far down in the direction of the flow and you will find that the cross section of the fluid that is flowing and also its velocity are constant, okay? So what I mean by that, if you look at this picture here, if you were to calculate the cross section of the fluid here, you will find that it is the same as the cross section of the fluid there. And if you were to calculate the velocity of the fluid at this position, you will find it to be the same here and everywhere along the pipe, okay? The velocity of the flow is constant. And also anywhere along the pipe, if you were to try and calculate the cross section, you will get the exact same number, okay? So that is what we refer to as a uniform flow. That is a flow where the cross section of the flow and its velocity remain constant throughout the pipe, okay? Very important. And then after that, we have what we refer to as a steady flow, okay? Now, with a steady flow, the velocity and the cross-section may change along the pipe. However, at individual locations, the velocity and the cross-section remain constant. Okay, so if you look, for instance, at a pipe that has got this shape, of course, you can see that the cross section, if the fluid were to flow inside of this pipe, then the cross section of the fluid wouldn't remain constant. Here, you will have a bigger cross section than you have here. Okay, so it's not constant throughout the pipe, and also the velocity of the flow wouldn't be constant. Okay, where you have a big cross section, the velocity is lower. Where the cross section is smaller, the velocity will be higher. Okay, so this flow here is not uniform. Okay, but it is a steady flow. So what we mean by a steady flow is that although the cross section is varying in the direction of the flow, it's not remaining constant, and the velocity also is not remaining constant. However, if you were to look at individual locations in the flow, then at those locations, the cross section will always be constant and the velocity will always be constant. So what I mean by that is that if I were to look at a cross section maybe somewhere here, the velocity of the flow at this cross section here will always be that number that you will get. Even if you come 5 minutes later and the flow and the water is still flowing, but if you come and you try and calculate the velocity at this location, it will always be the same value that you had 5 minutes ago, okay? And it will remain that value, okay? So, and the cross section also here will remain the same cross section even if you come 10 minutes later. So although the cross section is varying in the direction of the flow, it is not constant, and the velocity also is not constant. However, at individual locations, if you do your calculations, you will find that at that location the cross section is always this, and also the velocity is always that. Okay, so that is what we mean by a steady flow. And then the last term we're going to speak about is an unsteady flow. Okay, a flow that is not steady, it's unsteady. And so when you have an unsteady flow, the velocity and the cross section vary with time. Okay, so the cross section of the flow will not remain the same thing at a specific location, and also the velocity will not remain the same thing at a specific location. A good way to see that is when, for instance, you have a pipe in which you have a fluid that is flowing, but that fluid is not fully filling the pipe. Okay, so because the fluid is not fully filling the pipe, then at different times you will have different cross sections for the same location. So for instance, at this location here, if I come now, because the fluid is not fully filling the pipe, the cross section that I will get may be what you see on the screen. But if you continue to allow the fluid to flow, if you come 5 minutes later, since the fluid is not fully filling the pipe, then you will have a different cross section for the fluid at the same location. So you can see now that although it is the same location, but the cross section of the fluid is changing, and also its velocity is changing at the same location, then you will say that the flow is not unsteady. Okay, so this is very easy to understand if you think of water flowing through a pipe, but the water is not fully filling the pipe. So at a specific location, if you try to measure the cross section of the flow, it will not be the same if you come 5 minutes later. Okay, so in a situation like that, then the flow is unsteady, and even the velocity of the flow at the same location will not be the same if you come and measure it sometime later. Okay, so that's what we will refer to as an unsteady flow. Now, as a recall, I will bring some of the stuff that you might have learned in fluid mechanics N5. The first thing is the flow rate, okay? Now, the equation for the flow rate is Q is equal to A multiplied by V, okay? Now, Q is actually the flow rate. Sometimes it is also referred to as the rate of flow, okay? But we know this equation. A is the cross-section area and V is the velocity. Okay, so Q is equal to A multiplied by V, and the unit for the flow rate is cubic meters per second, but sometimes people also like to use liters per second. Okay, so if you want to convert between the two units, you just need to remember that 1 cubic meter is equal to 1000 liters. Okay, I repeat, 1 cubic meter is equal to 1000 liters. And so continuity, okay, so this is what we're going to speak about now. So basically, when you're dealing with a flow that is uniform and a flow that is steady, the amount of fluid that is entering a system must be equal to the amount of fluid that leaves the system. Okay, so that is what we refer to as continuity. Okay, and a good example of that is this pipe that branches out in two directions. And so the amount of flow that comes in here must be equal to the sum of these two flows, although it is branching out in these two directions, but the amount of flow that will come out here plus the flow that comes out there must equal the flow that got into the system. Okay, so that is what we refer to as continuity. It always applies when you're dealing with flows that are uniform or steady. Okay, so whenever we do our calculations, we will often be dealing with a steady flow, and for that reason continuity will apply. Okay, and so Q1 is the flow rate here at 1, okay, must be equal to the flow rate that is leaving at 2 plus the flow rate that is leaving at 3. And of course, if you want, you can replace Q1, Q2, and Q3 by the expression of the flow rate equation. Okay, so A1 V1 will be equal to A2 V2 plus A3 V3. Okay, the next thing I am going to talk about is the wetted perimeter and the wetted area. Okay, so what do we mean by the wetted perimeter? This is the perimeter that gets wet by the water as it flows through the pipe. The wetted area is the area that gets wet by the water as the water is flowing through the pipe. So a good way to see that is by looking at this picture here. So now here you have a pipe, okay, and this pipe has water flowing through it. So the inside of the pipe, of course, is going to be wet, okay. So now if we want to calculate the wetted perimeter, so what we will need to do is just look at the cross section. And it is important, first of all, to understand that we are dealing with a case where the pipe is completely full, okay? So the water completely fills the pipe, because of course, if the water is not completely filling the pipe, there may be some surface area inside of the pipe that is not being wetted by the water, okay, that is not being touched by the water. And so in this case we assume that the pipe is completely full, so the whole inside area of the pipe is wetted by the water. Okay, and so first let us look at the wetted perimeter. So what is the wetted perimeter? The wetted perimeter is basically just the perimeter of the cross section of the pipe. So if you look at the cross section of this pipe, it is a circle, okay? That is what the cross section of the pipe is. And so if this circle has a diameter d, and if we have to find the perimeter of a circle, the equation is very simple. It's pi multiplied by d, okay? Or if you want, you can say 2 pi multiplied by the radius, but I prefer pi multiplied by d. Okay, so the wetted perimeter is basically the perimeter of the cross section of the pipe. The wetted area is now the area of the pipe that is in contact with the water. And so to be able to calculate that area, you can just assume that we took a knife or a razor and we cut the pipe on top here, okay, and then we opened it in such a way that it becomes a flat thing on the ground, okay? And so if you do that, the shape that you're going to get is a rectangle, okay? So if you cut a pipe and then you open it up and you make sure that it is flat on the ground, the shape that you will have on the ground will be a rectangle. And so the one side of the rectangle will be the length of the pipe, okay? And the other side of the rectangle will be the perimeter of the cross section, okay? It will be that perimeter of the cross section, okay? And what is the perimeter of the cross section? It's just pi d, okay? So that side will be pi d. So now if we want to find the wetted area, okay, it's the area of that rectangle, because the whole inside of the pipe is wet. As we said, this pipe is completely full with water, okay? So this whole area is wet. So to find the wetted area, you just need to find the area of this rectangle. And so if you do that, what you get is L multiplied by pi d, or if you want, you could say pi dl. Okay, so that is the wetted area. It's very important to remember these, because we're going to use these expressions throughout the course. And so very, very important to know what we mean when we say wetted area, wetted perimeter. Very important to know what we mean. So the next thing we're going to talk about is the hydraulic mean depth, also referred to as the hydraulic radius, okay? And this is simply the ratio of the cross-section area divided by the wetted perimeter, okay? So we use the letter M to refer to the mean depth, or the hydraulic mean depth, okay? We use the letter M, and it is equal to the cross-section area of the pipe divided by the wetted perimeter of the pipe, okay? Cross-section area divided by wetted perimeter of the pipe. And if you replace cross-section area by pi by 4 multiplied by d squared, and then you divide by the wetted perimeter, which is pi d, you do your calculations and you simplify, you will find that the hydraulic mean depth is just equal to the diameter of the pipe divided by 4, okay? This is a very important equation. Sometimes they will ask you to find the hydraulic mean depth. So all you will need to do is to divide the diameter of the duct by 4. Okay, that is very important. Now, we will speak about Bernoulli's theorem and Bernoulli's equation, okay? This is the most important equation as far as flow in pipes is concerned, okay? And so, first, let us look at Bernoulli's theorem. In fact, I have seen that in some of the exam questions, they will ask you to state Bernoulli's theorem, and the question can be 2 marks. And so what is Bernoulli's theorem? It's actually very simple. Bernoulli states that in a closed system, that